Hi, my name is Alexander Ray, and I am the team lead for Cal Poly Pomona's AVSI competition team. I am an aerospace engineering major, graduating in June 2018. This is my second year on the team, and my second year working with UAS Technologies. My role on the team is to ensure that all hardware and software systems integrate and perform correctly. On the flight line, I will be acting as the communication relay between the ground station and the safety pilot, as well as being the spotter for the safety pilot.
My name is Thomas Fergus, aerospace engineer, class of 2018. This is my third year on the AUVSI team and my third year working on UAS Technologies. My role on the team is software lead, and on the flight line, I will be operating the ground station.
My name is Matheus Pinheiro, aerospace engineering major, class of 2019. This is my first year working on the AUVSI project and my second year working with UAS Technologies. My role on the team is to develop the image recognition software, and on the flight line, I will be operating the ground station.
My name is Andrew Moffett, and I'm an aerospace engineering major, class of 2021. This is my first year working on the AUVSI project and my first year working with UAS Technologies. My role on the team is to develop software for obstacle avoidance, and on flight line, I will be operating the antenna.
My name is Bryce Satterfield. I'm an aerospace engineering major, class of 2020, and this is my first year working on the AUVSI project and my first year working with UAS Technologies. My role on the team is to develop an algorithm to detect and classify objects, and on the flight line, I will be operating the ground station.
My name is Daniel Banowski. I'm an aerospace engineering major, class of 2020. This is my first year working on the AUVSI project and my first year working with UAS Technologies. My role on the team is to develop an algorithm to detect and classify objects, and on the flight line, I will be operating the ground station.
My name is Michael Doan. I am an aerospace engineering major, class of 2021. This is my first year working on the AUVSI project and my first year working with UAS Technologies. My role on the team and job on the flight line is to maintain and set up the vehicle prior to flight.
My name is Chris Hamilton, aerospace engineering major, class of 2021. This is my second year working with the AUVSI project and my second year working with UAS Technologies. My role on the team and on the flight line is to maintain and assemble the aircraft.
My name is Ronald Lim, mechanical engineering major, class of 2021. This is my first year working on the AUVSI project and my first year working with UAS Technologies. My role on the team is to develop 3D printed parts for the vehicle, and on the flight line I will be assisting with the vehicle setup.
My name is Tristan Sherman. I am an aerospace engineering major, graduating with the class of 2019. This is my first year working on the AUVSI project and my fourth year working with UAS Technologies. My role in the team and on the flight line is safety pilot.
This year's vehicle configuration features a twin-boom inverted V-tail airframe and utilizes an electric pusher power plant. The airframe is primarily made of styrofoam with some wooden reinforcements, aluminum landing gear struts, and carbon fiber wing spars. Modifications to the airframe were done by designing parts in SolidWorks and 3D printing them with PLA plastic. Parts that were created using 3D printing include the camera gimbal arms and support, the payload mechanism support structure, and the bullet mount. A pickstock is used as the flight controller for this aircraft, with modifications being done through Mission Planner and Mavlink. The camera is the Grasshopper 3 from Point Grey, and it is secured by the camera gimbal and oriented using the third-party gimbal controller. In terms of power management, 2 4-cell batteries are used to power the motor, 1 3-cell battery is used to power the pickstock, 1 3-cell battery is used to power the camera, and 1 last 3-cell battery is used to power the bullet and camera gimbal.
The team is using a modified version of Mission Planner to achieve this year's tasks. The tasks include interoperability, collision avoidance, bottle drop, and target detection, classification, and localization. For collision avoidance, the obstacles are being pulled from the server and passed to the avoidance code, where the Unity game engine is utilized to plan the optimal flight path. For bottle drop, a MATLAB script is called from the Mission Planner C# code to determine the optimal drop location. And for target detection, classification, and localization, Python is utilized to determine the presence of a target within the camera's field of view. The target is then ran through a neural network to determine its characteristics. All targets submitted to the server can be checked and altered from the Mission Planner application.
We will be attempting all of the tasks in obstacle avoidance and air delivery. We are 70% confident in the aircraft's ability to avoid obstacles, and 80% confident in the aircraft's ability to drop the payload into an area within 35 feet of the target. All of the tasks for autonomous flight will be attempted apart from autonomous takeoff and landing. We are 90% confident in the aircraft's planned tasks for autonomous flight. For object detection, classification, and localization, we will be attempting all tasks apart from the off-axis target. We are 92% confident in our ability to achieve the planned object detection, classification, and localization tasks.
The types of developmental testing that were applied include simulation, unit testing, performance testing, stress testing, and integration testing. Obstacles were simulated using the Unity game engine to optimize the pathfinding process and visualize how the obstacle avoidance code will work during the mission. Unit testing was applied on various codes, such as the image detection, to see if proper output is given for a sample image. Performance testing was conducted for the GPS localization and bottle drop code to assess the limitation and accuracy of the code relating to the target. During the flight test, a stress test was performed for the air delivery to make sure the bottle will explode on impact. Integration testing was achieved by making sure the obstacle avoidance code will properly communicate with the PIXOC.
The team has conducted 27 autonomous flights. Because of our choice to do manual takeoff and landing, we spend an average of 90% of flight time in automatic mode. Each day the plane is flight tested, we run calibration for GPS, magnetometer, and accelerometer and tune the aircraft's PIDs to improve its response to external disturbances.
For waypoint accuracy, we use a 6-foot radius for our search waypoints because the system makes flight adjustments to stay on the path. Other factors such as wind could offset the system, making it miss its waypoint. If it goes unchanged, the system would repeatedly try to reach the waypoint. With the 6-foot radius, it gives the system a tolerance area to stay within so that it does not keep flying in circles. Due to the system being fixed-wing aircraft, it is possible for it to miss a waypoint. If the system misses a waypoint, it will go back to the missed waypoint before continuing on to the original flight path. Accuracy for hitting these waypoints is being evaluated through flight testing.
For the obstacle avoidance code, the Unity engine was used to virtually simulate the field. Then, by updating Unity with the positions of the aircraft and obstacles, it returns a calculated waypoint for the craft to follow. This allowed the software to be tested in isolation without risking the vehicle. Simulations were ran with up to 16 moving obstacles on the field at once. However, the aircraft usually only needed to avoid 2 to 5 in one run. For normal testing and randomly placed obstacles, no failed runs were observed. However, clusters of obstacles can cause unnecessarily increased flight time. Additionally, failed runs were only observed when the obstacles were pre-programmed with exceptionally difficult patterns, such as all converging or chasing the aircraft. Excluding these exceptions, the obstacle avoidance code has achieved a success rate of 100%.
To test the camera system, we captured the targets at ranges exceeding 100 feet in order to simulate the size of the targets in flight. To maximize the resolution of the camera at 1640 by 940, the camera will be recording at 9 frames per second. Handmade targets were created to better test the camera in both static image tests and video tests. The camera was also tested in various lighting environments to simulate various weather conditions that may occur during the competition.
In order to correctly detect objects, we implemented a simple algorithm for identifying regions of interest. We created test objects for shapes and letters we believed would be harder to detect and tested our algorithm on images of these shapes taken from approximately the distance the vehicle would be from the ground. Using this data, we were able to adjust our algorithm to work with 100% accuracy on our testing data. To correctly classify objects, we implemented a pre-trained convolutional neural network and retrained the final layer. A script allowed us to produce over 362 gigabytes, around 500,000 images, similar to those that we would find in practice. Splitting 10% of that testing data into 80% training and 20% testing allowed us the ability to test the effectiveness of the convolutional neural network. After training on 10% of our total images, we ran our testing images through our retrained network, achieving an accuracy of around 92%, showing that our training had worked effectively.
The purpose of the GPS localization code is to acquire the GPS location of each target that has been confirmed by the image recognition software. It uses the pixel location of the target on the image in which it was identified, the plane GPS location, heading, and altitude at the time of identification, and the camera's field of view. With these parameters, the code outputs each target's GPS location. The limitations of the code are that it assumes that the camera is pointing straight down at all times and that the altitude of the plane is constant. Through testing, it has been determined that the code is accurate within 3 feet.
The air delivery code has been tested 17 times to date. In each test, the bottle broke on impact, spilling its contents. One limitation with this testing is that the landing site was always a hard surface, such as concrete. Testing on whether the bottle will break on contact with a soft surface, like grass, will be conducted at the next flight test. In the final flight configuration and code structure, the average offset from the target was 35 feet. This accuracy was achieved using MATLAB to optimize the drop location by solving the set of nonlinear equations that characterize the bottle's descent through the air. This equation solver takes the speed and direction of the wind, the aircraft's velocity, and the altitude the bottle will be dropped from to solve the bottle's equations of motion for the optimal drop location. Full mission tests have been conducted to ensure that our target objectives are met. We are capable of autonomous flight with waypoint navigation, air delivery, and target imaging detection. The UAS hit all of the waypoints with an average radius of 6 feet. The bottle averaged 35 feet from the target and broke during all full mission tests. The target detection software was able to detect and classify targets with a 92% accuracy. From these tests, it was determined that the aircraft will need to land halfway through the mission in order to change motor batteries, due to the limited flight time. Collision avoidance has not yet been tested in the air. The concepts in which waypoints are rewritten into autonomous mode have been tested in flight. This concept is something that will be used for avoiding obstacles. Overall, the full mission test determined that we are able to complete our targeted objectives. The maximum percentage that is achievable in this year's flight demonstration is 97.2%. This number comes from the system not being able to complete autonomous takeoff, landing, and off-axis target search. The score we expect to receive is 93.8%. This comes from the possibility of bottle drop being off by 35 feet, waypoint navigation off by 6 feet, and geolocalization being off by 5 feet, in addition to the maximum percentage.